Chemical properties alert us to what type of reactions a compound can undergo. Reactions change the bonding pattern, whether it's going to be making multiple bonds or breaking bonds, adding heteroatoms, or splitting molecules apart. So that ability to change from one organic family or functional group into another is what we're going to investigate as the chemical properties for the organic compounds in this course. There are different types of reactivity, some that we'll investigate a lot more than others, but these are signs or ways we know that a chemical reaction may be taking place. Flammability, toxicity, and acidity are just some ways in which we can track these chemical properties. A lot of organic reactions occur through oxidation reduction processes. We have talked about oxidation reduction in our previous material, and the same principles apply here. So remember that electrons are shared within the bond between those two elements. And then we need to look at the electronegativity values to help us understand which elements control electrons within that bond. That goes back to looking and defining the bond polarity for each of these compounds. So in the process of oxidation, carbon is losing control over the electrons in a bond between carbon and oxygen. Carbon has that electronegativity value of 2.6 and oxygen has a 3.4. That difference is 0.8. That tells us we have that polar covalent bond, and with oxygen being more electronegative, it's going to have more control over those electrons. For carbon to be reduced, it needs to gain control over the electrons. So when we see an increase in carbon-hydrogen bonds, that is a sign that carbon is being reduced. With carbon's electronegativity value of 2.6 and hydrogen's electronegativity value of 2.4, that has a 0.4 difference. We do refer to that as a non-polar covalent bond. However, because carbon does have a slightly higher electronegativity, it gets a little bit more control over the electrons in hydrogen, just not enough to really create a dipole moment. We're going to be looking at combustion reactions as our first type of redox with our organic compounds. Using methane as our first example. Methane is the most simple organic compound there is. Even though carbon and hydrogen do have a slight electronegativity difference, it is really not enough to create that dipole moment. Therefore, we say that carbon and hydrogen have about equal control over those electrons. However, when we look at the oxygen within the carbon dioxide compound, as we determined, oxygen has a higher electronegativity and is going to take more control of the electrons in the double bond than carbon. This electronegativity difference creates those polar bonds, which then we can use dipole arrows to help us represent where the electrons are being pulled to. For this course, we do not need to determine the oxidation state of each element within our organic oxidation reactions. We are going to just track the changing bonds. And we're going to track the reacting carbon. Here in methane, we want to determine how many carbon-hydrogen bonds exist, because that tells us how many potential sites for reaction can occur. In methane, we've got 4 carbon-hydrogen bonds. Then we want to look at the carbon-oxygen bonds. In methane, there's 0. Looking at the carbon on the product side, there are no more carbon-hydrogen bonds, and our carbon-oxygen bonds went up to 4. So as methane was reacting with oxygen through the process of combustion, what we see is that carbon undergoes oxidation. That is what we need you to be able to do with redox reactions in our organic course. Now try one oxidation reaction on your own. Write the products of this combustion reaction. You can look back at the previous one because it's always the same two products for a complete combustion reaction. And those are the only types of combustion we are going to focus on. You do need to balance these combustion reactions, so going back and practicing how to balance it. If you notice in the previous problem with methane, we had our coefficients there already. Then track how many carbon-hydrogen bonds there are in the reactants and how many carbon-oxygen bonds are in the products. Pause the video, try this on your own. Here we have ethane and we have oxygen. We know that it's going to make carbon dioxide and water. Hopefully what you got was 2 ethane, 7 oxygen, 4 carbon dioxide, and 6 water. If you did not get that, go back and kind of see if you can work backwards to see where you may have incorrectly balanced these compounds. In the ethane, we have 6 carbon-hydrogen bonds and 0 carbon-oxygen bonds. In the product, we have 0 carbon-hydrogen bonds and 4 carbon-oxygen bonds. Again, we are seeing that increase in the number of carbon-oxygen bonds, which means carbon is undergoing oxidation. This is what you need to be able to do with our organic combustion reactions.